Okay, hello everybody. Hope everybody's doing well today. Thank you for joining our next video lesson. We are in Unit 8 still. Let's recap. We have learned some more additional formulas in rectangular form. We've learned some stuff in parametric form, and we have learned some stuff in vector form. That leaves one last type of equation, and that is polar. All right, polar is fun, especially when it comes to some calculus problems. So today is all about recapping on what you should already know about polars from pre-calculus. Now I realize that a lot of people didn't have a chance to learn that because of the cutoff last semester. So I'm going to try to hit some of the recap in a little bit more detail than usual. But if you can understand what I'm talking about today with the recap, then you're going to be all set for doing some calculus. Okay? All right, so a polar equation is honestly the same as a rectangular equation. The only difference is just how we express where we're going to, if that makes sense. So let's think about it this way. Let's treat this point right here that I'm highlighting as the pole or our origin. And honestly, it's still the same origin as if we were on a rectangular, X and Y coordinate plane, okay? But instead of saying like we're going to go over X and up Y to a point, okay, that's what we're used to doing, right? We're used to saying go over X, up Y, like a coordinate point. We're now going to discuss going a certain radius length and a certain angle length to get there. Okay, so the radius is going to be from the origin to my new point, so it's how far out from the origin that I go. And the angle measurement is going to tell us how far that I travel from what we call our initial axis here to our terminal side. Okay, and the initial axis is going to be our what we usually call our x-axis, and the terminal side is just going to be that radius length. Okay. Now we're going to be plotting a lot of these points here in a second, but just a couple things that I would like to note before we move on. That if our radius is positive or greater than 0, r is in the same quadrant as theta. And if r is less than 0 or negative, r is in the opposite quadrant as theta. Okay, so we're going to do a bunch of problems practicing dealing with points in polars, equations in polars, and this is all going to lead to some calculus in our next lesson. All right. So let's look at a polar graph real quick and talk about graphing points. Okay, let's start by looking at a polar graph, a polar plane that we can plot some points on, and how we can graph specific coordinate points, right? So it looks scary. I mean, it looks different, but if you just draw a vertical line down the middle and a horizontal line through the side there, I want us to understand that this is nothing more than just an X and Y coordinate plane, okay? It's just we're plotting points differently, okay? It's no longer X and Y, it's now R and theta. So this point right here is R, comma, theta. Now, it's not the worst thing in the world to do if you're comfortable doing like unit circle stuff, for instance. Like this is kind of similar to that. Okay. All right, I'm going to label the axes pretty similar to how we do the unit circle. So like right here in the middle, I'm going to make this my pi over 4. And remember, like when I'm saying pi over 4, this is an angle measurement from my initial side, just like on a unit circle. So I'm going to treat it with the same angles that I do on a unit circle. So I'm going to say like pi over 6 right here, pi over 3 right here, okay? Pi over 2's up here. So, I mean, again, the axes are pretty similar to a unit circle. So we'll call this pi, maybe 3 pi over 2. You kind of get the idea here. And we'll call this all the way around to 2 pi or 0, right? Okay, so if I said 5 pi over 4. That means that we're going to travel from our initial side 5 pi over 4 radians all the way around, and we're going to have a radius length from the origin of 1. So let's start, I always like to start with the angle. So let's start with 5 pi over 4. Where is 5 pi over 4 from this initial spot right here? Okay, well, we got 1 pi over 4, 2 pi over 4. I mean, right here is 3 pi over 4. Right here would be 5 pi over 4. Okay, so again, it's the same radius from the unit circle. I'm traveling all the way around to this point right here. And the point that I like actually plot the point at is 1 radius length from the origin. Okay, now the origin's right here. Each circle is supposed to represent 1 radius length away. So I know this is going to be hard to see. I'll change colors. How about right here would be 1 radius length on the theta value, 5 pi over 4. Okay, so I'll call that point A. Okay, and I encourage you to pause the video, try to do B, try to do C, try to do D on your own if you can. I'll give you a second or two to pause if you need to. But otherwise, I'm just going to kind of move on with it. Okay? So this next one here, so we got 2, 3 pi. So that's a radius length of 2 and a theta value of 3 pi. All right, so let's start. I like to start with the radius part, or the theta part first. So 3 pi is like going around the circle once and then half a circle over. 3 pi is the same spot as right here at pi, right? Remember, if you have an angle measurement over 2 pi, you can always subtract 2 pi to find a coterminal angle between 0 and 2 pi. I feel like I'm saying pi a lot. But anyway, the angle measurement of that is right here. Now, the radius measure from the origin is 2. So I'm going to go 2 like circles away from the origin, and my point is going to be right here. This is point B. Okay. All right, let's try C. So we got 2 negative pi, or negative 2 pi over 3. And again, you're used to doing unit circle stuff. The negative just means that we're going the opposite way from our initial side here. So if you feel comfortable traveling backwards, do that. But just like in part B, if you don't, you can always add 2 pi to this, which I'll say 6 pi over 3, to figure out an angle measurement between 0 and 2 pi. It's just whatever you're comfortable with. So for instance, like negative 2 pi over 3 is the same thing as, what would that be, 4 pi over 3? Okay. So it's like going to the same spot as 4 pi over 3, which 4 pi over 3, if you count around the circle, would be right here. Okay. Now, if we have trouble plotting radian measures around the circle, we might need to practice that a little bit, but again, I'm just using the same radian measures from our unit circle. So there I am at 4 pi over 3. And a radius length of 2 would be about right here. Okay, I'll call that point C. All right, let's try one more point. So we got 3 pi over 4, okay, which is the same radian that I was just at. And we're doing negative 3. Okay, so we're traveling all the way to 3 pi over 4. This is the blue line that I just highlighted right here. But notice the radian. The radius is negative, okay? So how we deal with a negative radius is, instead of traveling along the theta value here, this theta line, we are going to be going backwards on the line, okay? So if I'm at 4 pi over 3 here, instead of moving forward 3, I'm going to move backwards 1, 2, 3 to this point right here, okay? To this point right here. And mistake number 1 just happened in the video, so we can go ahead and check that off the list there. This is not 3 pi over 4, that's 4 pi over 3. 3 pi over 4 is right here. Dang it. So let's restart that. Instead of moving to that line, we should be at the line 3 pi over 4, which is right here. Moving backwards along that line would be 1, 2, 3. We should actually be right here for point B. Yeah, that's my bad. I read that as 4 pi over 3. instead of 3 pi over 4. So that's awesome. But anyway, that's a refresher on how to graph polar points with your r value and your theta value and all that good stuff. Okay. Let's move on to some other polar stuff that we need to know how to do. All right, I love this question here. It says, in the Cartesian coordinate system, let's stop right there. You're probably like, what the heck is the Cartesian coordinate system? The x and y coordinate plane that you're used to like graphing in rectangular calculus, that x-y coordinate plane is called Cartesian coordinate system. I think it was some dude that was named, I really don't know, but it's called the Cartesian coordinate system. Every point has only one representation, right? That one point is over x of y. Okay, I mean, that's just how you plot points. You go over an x value and you go up or down a y value, right? But the cool thing about polar coordinates is that each point can have many representations. And honestly, if you really want to think about it, it could have an infinite amount of representations. For instance, let's consider the point 1, 5 pi over 4. That's a radius of 1 and a theta value of 5 pi over 4. So let's look at where that is on our graph. Okay, so here's my coordinate axes here, and I'll just draw like I'll just draw a generic circle right here. We'll call that circle just a radius of 1. 5 pi over 4 is in the third quadrant. It's actually halfway in the third quadrant. It's right here. Okay, 5 pi over 4. Okay. Now, there's multiple ways to represent this same exact point in polar coordinates. Okay, 1, 5 pi over 4 is one of them. All right. Well, what's another way we can do this? Instead of traveling a positive theta value around the circle to get to 5 pi over 4, what will be the radian measure as I go backwards from the origin to 5 pi over 4? How many radian measures am I traveling backwards? Turns out that's going to be negative 3 pi over 4, right? If I were to travel negative 3 pi over 4 radians from the initial side here at the origin, I would be over here at the same point as 5 pi over 4 with a radius of 1. So instead of going forwards, I can move backwards. Both these points will take me to the same spot on the polar graph. All right, well, what's another way to do this? Well, how about instead of thinking of a positive and negative theta value, what about a positive and negative radius value? Like right now, radius is positive 1. What about, like, for instance, if I go like right here on the unit circle, right, or on this polar graph? If I travel here, that's the same thing as going to pi over 4. Okay? Now, instead of going to positive 1, then I could travel to negative 1, and I would go backwards along that line and end up at the same spot that I've been talking about, right? So I could say negative 1, comma, pi over 4. Okay? So what's another way that I can get to this point, pi over 4? Instead of going in the positive direction, I could also go in the negative direction. I could travel all the way around in the negative direction until I get to pi over 4. So another way to get to pi over 4 is to say negative 7 pi over 4. That would be me traveling backwards in the negative direction and reaching the same point. So I could also say negative 1, comma, negative 7 pi over 4. Okay. So there's 4 right there. Two of them that would get me to this top right corner, and then traveling backwards with a negative radius. And then 2 of them that would get me to the actual spot with a positive radius. Okay. So, pretty cool. I mean, technically you can give me an infinite amount, just considering how many times you can go around the unit circle, but usually we can write it as about 4 of them. But we will definitely be practicing that more as well. Okay. All right, some other stuff that you need to know here. I keep saying that polar coordinates are graphed really on the same graph as the x and y coordinate plane, right? It's just we're getting to a point using different measurements. We're using a radius and we're using a theta. So with that being said, since we can, like, since we're on the same graph, we are able to, like, change polar equations to rectangular equations. Okay? So like if I want to go from polar to rectangular, that means that I'm given some form r comma theta, then I can use this logic right here that x equals r cosine theta and y equals r sine theta to change it to a rectangular form. Okay? The whole goal is to eliminate r and theta. So I want you to add this to your list of, I guess, formulas, knowledge, whatever you have. Okay, I mean, again, this is some review of pre-cal here. And we can talk about exactly where these identities come from. And when we talked about it in the past, this is the same thing as circle parameterization. Okay, so it goes along that same exact logic. All right, understanding the fact that it's just Pythagorean theorem. Okay, but if I want to go from, say, rectangular to polar the other way around, so if I want to go from x comma y to r comma theta, here's the two formulas that we would use. The fact that r squared equals x squared plus y squared, and the fact that tan theta equals y over x. We also say r would equal the square root of x squared plus y squared. Okay? All right, the reason that this works, the reason that this relationship works is if you consider the graph, okay, if you consider the x and y coordinate plane, and let's talk about this specific point right here. Okay? The reason these two identities are able to relate is because of how we can get to this point on this graph, right? We can go over x and we can go up y, over x and up y, right? Or we can talk about this point in terms of a radius length, right? A radius length and a theta value, right? We can talk about it in terms of a radius and a theta. So notice that this point can be described two ways, x and y, or r and theta. And it's because of what we know about how theta and r and x and y relate on a right triangle that we're able to come up with these identities to substitute from one version to the other, right? I mean, simply put, like, for instance, r is the hypotenuse. And we know that a hypotenuse, r squared, is equal to the two legs squared and added together, right? So that's how we get that identity. Like, for instance, also, like, I'll give you another example. Like, we know that y, okay, y, in terms of theta, would be like y would be the opposite, and r would be the hypotenuse. Okay, so hypotenuse and opposite, that would be sine. So we got that the sine of theta equals opposite over hypotenuse, or that y equals r sine of theta. So that's how we get this identity, y equals r sine of theta. And the same argument can be made for x equals r cosine theta. So that's kind of where all these formulas are coming from here. Let's look at some examples with this. It says, convert the point 3, 5 pi over 6 from polar to Cartesian coordinates. Okay? So like right now I'm given an r and I'm given a theta. Okay? I want to move this to an x and a y. Well, we know that any point can be represented as both. It just depends on how you want to get to it, right? And we know how to go from one to the other now. Okay? We know that x equals r cosine theta and that y equals r sine theta. So all you got to do is just plug r and theta into both of those, and you got your x and your y. It's that simple. Okay? So if I plug r and theta into r cosine theta, that's 3 cosine of 5 pi over 6. And at the bottom here, it will be 3 sine of 5 pi over 6. Okay? So my coordinate point would be, right, the cosine of 5 pi over 6. Think about your unit circle. That's in the second quadrant, so it's going to be negative. So it's going to be negative, let's see, square root of 3 over 2. So that would be negative 3 square root of 3 over 2. And the sine of 5 pi over 6, so again, just kind of go along the unit circle there. In the second quadrant, it's going to be positive. Your reference angle is pi over 6, yada, yada. You should be good at unit circle. That would be 1/2. Okay? All right. So let's see here. We now just went from polar to a Cartesian point. What about the other way around? What if I have a Cartesian point, so an x comma y, and I want to convert this to a polar point, which is r comma theta. Okay. Well, again, we have two formulas for that. The r value is equal to the square root of x squared plus y squared. That just comes from Pythagorean theorem. And we also know that theta is going to equal the tan inverse of y over x, or in this, well, I'll just write y over x. Okay. All right, so for r, that's going to be the square root of 3 squared plus 2 squared. And for theta, that's going to be the tan inverse of 2 over 3. So that simplifies down to the square root of 13. And you can do tan inverse of 2/3 in your calculator because, well, that's not some exact value we should know. And that ends up being approximately 0.588. Okay? All right. So just a couple more, and then we will call it. I'm getting to my 30-minute mark here, so let's see how much more we can get. All right, let's look at another example of something polar. It says, represent the Cartesian coordinates, okay, 1, -1, in terms of polar coordinates. It is important to choose theta so that the point r theta lies in the correct quadrant. Okay, so let's think about this. If I do the point 1, -1, here's 1, here's -1. Okay, that's me going to the right one and then down -1, right? Okay. So to get all the way around to this point here, right? We're starting, like, I can choose a couple points here if I wanted to, but I like to think of it as that I'm going around the circle all the way to this point right here, right? You can represent that as a positive value or a negative value, right? Positive value if you're going all the way around the circle, or a negative value if you're coming backwards. So, I mean, I'll leave that up to you. We said in an earlier slide that there's multiple ways to represent this point. But let's start with the r value. The r value is going to be the square root of x squared plus y squared. And my theta value is going to be equal to the tan inverse of x over, or I'm sorry, y over x, or -1 over 1. Okay. All right, so for the r value, it's going to be the square root of 2, it looks like. And for the tan inverse, okay, so the tan inverse of -1, you can type this in the calculator, but this is an exact value that you should know. If you think about inverse trig, tan inverse of -1 is -pi over 4, okay? -pi over 4. So you can write this out exactly like we just came up with. -pi over 4 just means that I'm going backwards to this point, and positive square root of 2 means I'm going forward to this point, so that works out. So you can put the square root of 2, comma, pi over 4. Okay? All right, I got, let's see, I'm at 23 minutes. I don't want to cover too much more. I'm going to do this last example, and then I think I'm going to call it after that because I don't want to go too far without you, and I would like to be able to set us up to do some calculus together as well. So we'll end with this last point. I think this will be a good stopping point. It says, find the polar equation of the line that goes through the origin and has a slope of 3/2. Okay, so let's draw that out real quick. It says, find the polar equation given the fact that it goes through the origin and has a slope of 3/2. So let's draw that out. The origin is right here. It's going to go through the origin, and it has a slope of 3/2. Okay, it has a slope of 3/2. So that means that we're going up 1, 2, 3, and over 2. So it looks something like this. Okay? So it wants me to find the polar equation of the line that goes through the origin and the slope of 3/2. So if I'm given this line right here, do you think that you could tell me the equation of this line in rectangular form or from the Cartesian plane? And absolutely you should be able to, right? It's a line. We got a couple points here. We got a slope. This is just y equals my slope, 3/2 x, plus my y-intercept of 0. So this is the rectangular form of this. Okay? Now, if this is the case, to go from rectangular to polar, well, it's just going to be some simple substitution, right? So we're going to use the same substitutions that we used to go from points to other points. Now we're going from equations to another equation. So, but I still use the same exact identities, right? Y is the same thing as r sine theta, and x is the same thing as r cosine theta. Okay. Now, just like with x and y equals equation, we want to get it y equals. Same thing with an r and theta equation. Usually you want to get it as an r equals equation. But if you notice in this case, the r's just divide out. So we're left with sine of theta equals 3/2 cosine theta. Okay, well, since I don't have an r, let's try to get theta by itself. So let's divide both sides by cosine. We're left with sine of theta over cosine theta equals 3/2. And we know that sine theta over cosine theta is the same thing as tan theta equals 3/2. And lastly, if I want to get theta by itself, we can do tan inverse. So I get that theta equals the tan inverse of 3/2. Okay. All right. So this will be the equation, and hopefully this makes sense because the thing is like theta equals, okay? Theta is just an angle measurement. Theta is just an angle measurement. So this is telling me one angle measurement is this angle measurement. It's not specifying the radius, so that's why we have this entire line right here. If I had given you just an r equals equation, I'm telling you a radius and not an angle measurement, so that would be like this. So that's r equals 4 would be a circle, and theta equals a number is just a line. Now, what sucks in calculus and the fact that you didn't have polars last year is the fact that I'm sitting here having to explain a week, maybe 2 weeks worth of lessons in one freaking slide. So bear with me on that. But we're going to review this a lot more as we go on to the calculus and polars. So when we get back together, we're going to learn how to graph an equation. We're going to refresh ourselves on how to transition between two different types of equations. And then we're going to actually finally jump into the calculus of polars, which is what I'm excited to get to. All right, well, you bear with me enough. So there's my smiley face, my heart, and my star. That's a terrible star. I hope y'all have a great day. I'll see you. Okay.